Okay, so let's start with this tutorial. First question is question number 3.12. So the question states to determine the causal signal x of n having the z transform. So x of z is equal to 1 upon 1 minus 2 z to the power of negative 1 into 1 minus z to the power of negative 1 squared, right? So there's typo error here. This 2 was supposed to be squared, right? Just supposed to be the power of this particular term, right? 1 minus z to the power of negative 1. So the first thing is to, in order to find the inverse z transform of this particular term, we first need to divide it into, I'll use partial fraction to separate this term, right? To separate the denominator. So performing the partial fraction decomposition, we get we get something like this. So we'll be having three values, right? A1, A2, A3, and the denominator will be z minus 2, holding upon z minus 1 and z minus 1 squared, right? So we'll be having three terms. So if we find z, these particular constants using partial fraction decomposition, we'll be getting A1 is equal to 4, A3 is equal to negative 1, and A2 is equal to negative 3, right? So basically, we can rewrite this as this, right? So basically, this whole term could be rewritten as x of z is equal to 4 upon 1 minus 2z to the power of negative 1 minus 3 upon 1 minus z to the power of negative 1 minus z to the power of negative 1 whole thing upon 1 minus z to the power of negative 1 whole thing squared, right? Then using the properties given on on page number 170 of your textbook, right? If you go back to page number 170 of your textbook, you can see there's a table that is given over here, right? This particular table could be used to find the inverse Z transform. So it has, as the question stated, that we need to find the causal signal, right? We need to determine the causal signal x of n for this particular Z transform. We use that. So the properties that we'll be using is a to the power of n u of n, right? That gives us 1 upon 1 minus a z to the power of negative 1 and n times a to the power of n u of n. The transform of this is going to give us a z to the power of negative 1 holding upon 1 minus a z to the power of negative 1 holding squared, right? Using these two properties, we can find the causal signal x of n of this particular z transform that is given to us, right? So doing that, we'll get x of n is equal to 4 to the power 4 into 2 to the power of n minus 3 minus n whole thing multiplied by of n, right? So that is basically our causal signal, right? 3.13, right? 3.13, the question states, let x of n be a sequence with the z transform x of z. Determine in terms of x of z the z transform of the following signal, right? A. So A is x of 1 of n is equal to x of n upon 2 if n is equal to even, 0 if n is equal to odd. So part A, so this signal that is given, so performing the z transform of this is basically x1 of z using the definition of z transform, right? We get x1 of n, z of negative n holding summed up from n is equal to negative infinity to infinity, right? Based on this, x of 1 of n is x of n upon 2, right? So basically we can substitute x1 of n with xn upon 2, right? For n is equal to even, right? While for n is equal to odd, everything is 0. So we don't have to perform the z transform of this 0. So basically the z transform of this is equal to 0, right? So we just need to perform the z transform of x of n upon 2. So using the definition, we can substitute that and we can get this, right? Using the z transform definition. And then what we can do is to rewrite this term in terms of k, right? We can replace n upon 2 is equal to k. So n upon 2 is equal to k. That is the substitution we can use. So based on that, we have to change the limits. So in this particular case, our limits are positive and negative infinity. So our limits will remain as positive and negative infinity. In place of n, we'll be using k, right? For n upon 2 replaced with k, we'll get this particular term, right? By substituting, we'll be getting this particular term. And then we can further evaluate this term as this one, right? We can further simplify this. We'll be getting x of k into z to the power of 2 into negative k, summed from negative infinity to positive infinity, right? So that will give us, you can say that this is a z transform. Again, this is in terms of z transform, but in place of z, it is z squared, right? So that it gave us x of z squared, right? In that particular case. So basically, x1 of z is equal to x of z squared. B, so part B, x of x2 of n is equal to x of 2n, right? So basically, again, using the z transform definition. So if we are finding the z transform at x2 of n, so we just need to replace x of n with x2 of n in this particular case. Using the z transform definition, we get this as the, I mean, we can rewrite that in terms of summation, and we'll get this particular term, right? And then we can see that x2 of n is equal to x of 2n. So we can replace x2 of n with x of 2n. So we will get this particular term. Based on this, we can again simplify this. We can rewrite it in terms of k, let's say. So in this particular case, we can write k is equal to 2n and change the limit and the variables in terms of k over here. So once we do that, we'll get this particular term over here. So this is, remember, we have substituted k is equal to 2n. So based on k is equal to 2n, we know that k is even, right? K is even. No matter what n is, it will be an even, it will be an integer value, n will be an integer value. So regardless whatever n value we get, k will be always even. So we know this, right? So based on this, we know that k is even. So we can rewrite this particular term, right? We can rewrite this particular term for any k value, right? We can rewrite it for any k value, right? As this. So you can see if we can rewrite this in terms of this, right? For any k value, right? So just in case, if it's k is an even number, this term will yield x of k, right? Remember this. This x of k can be rewritten as this for k is equal to even. So you can see if k is even, this k is even, this part will change into positive. So x of k plus x of k divided by 2 will just give me x of k. So basically we're getting this term back. So, but if k is equal to an even number, it will give us x of k minus x of k all thing upon 2. So that will basically 0. So we know that for k is equal to odd, the term will be 0, right? Okay, this whole term will be 0. So likewise, this whole term could be rewritten as this for any k integer value, right? We do not have to define that k has to be an even number. Over here, we do have to define that k is an even value, right? So basically, x of k could be rewritten as this for k is equal to even, right? We get this particular term, and then perform further evaluating this, we'll get 1 upon 2 summation from negative infinity or infinity of x of k into z to the power of half whole thing to the power of negative k, right? Plus, so basically just separating this again, half summed from k is equal to negative infinity to infinity, x of k, again this value, right? Further simplifying this negative 1 could be regrouped with this z and k taken out. So based on that, we have negative z to the power of negative half whole thing to the power of negative k. Right? So basically we get half of x, half multiplied by x of root of z plus half of half multiplied by x of negative root of z, right? So this is given in terms of the z transform of x2 of n in terms of x of z is given in terms of this, right? So this is what we get. Question number 3.14. Question number 3.14. Again, we just need to solve for the question that we need to solve is 3a, 3i, and j, right? I mean 3.14, a, I, and j, right? These three. So solving for that, again the question says determine the causal signal x of n if it is z transform x of z is given by, right? So this is the z transform. We need to find the causal signal x of n, right? Again, the steps are simple. I won't recommend you guys to use this particular method. The most simpler method is to decompose this signal using partial fractions. So we'll be getting, if we decompose this, we can see that this denominator could be written as 1 plus z to the power of -1 into 1 plus 2z to the power of -1, right? So this could, the denominators could be written, I mean, could be split, or what do you say, it could be uh, it could be factorized as these two, right? These two terms. So we could just find the coefficient in that particular case. So if we use partial fraction and decompose this, we'll be getting 2 upon 1 plus z to the power of -1 plus -1 whole thing upon 1 plus 2z to the power of -1. Again, going back to our table, 170, page number 170, we have the table over here. So you can see that for z is greater than the magnitude of a, right? In that particular case, as long as z is greater or falls on the outside boundary or towards the infinity part, that means it is a causal system. If region of convergence is inside a circle, so basically it is a anti-causal. So we'll be using these particular properties, right? All for z is greater than magnitude of a, right? So all these properties. So if we use these properties, we can, and we'll see that the causal signal, or basically the other way to analyze is that whenever we have u of n, right? Basically, whenever we have u of n on the positive side of the real axis, basically that signal is a causal system. While if it falls on the negative half of the plane or the left-hand side of the plane, it is an anti-causal, right? All these signals that has u of -n-1 are all anti-causal, right? All these signals are causal systems. You can see z is greater than a and it falls outside the circle, right? The region of convergence, if you draw a circle, the region of convergence of this, it falls on the outer circle. Wait. Okay. Anyways, using the properties of those that are given on this particular term, you can see that we just need to use this particular property, right? A of n, u of n. So we can use this property. This is a causal signal property, right? This particular term. So we can use that transformation. We'll be getting 2 into -1 to the power of n minus 2, -2 to the power of n, whole thing multiplied by u of n. This is a causal signal, right? That will get from this particular set transform, right? That is given. 3.14i. So again, in 3.14i, we get we get this particular signal x of z is equal to 1 minus half z to the power of -1, whole thing upon 1 plus half z to the power of -1, right? Plus, so this is the signal we get. What we can do is we can rewrite this signal, right? We can keep the numerator as it is, right? We can keep it as it is, and we can substitute using the property of 1 upon 1 plus half z inverse, right? Basically, this we can substitute x as x1 of z, right? So we can replace 1 upon 1 plus half z inverse with x1 of z. So we can rewrite this whole term in terms of this, right? And then based on this, we can see that we can if we expand this, we get x1 of z minus half into x z to the power of -1 multiplied by x1 of z. If we perform the inverse z transform on this particular term, we'll get x of n is equal to x1 of n minus half x1 of n minus 1. Remember, this z to the power of -1 indicates a delay, right? So it will be a delay in this particular signal, right? x1 of n. So if we do a direct z inverse the inverse z transform of this particular signal, we'll get x of n is equal to x1 of n minus half x1 of n minus 1. This is using the linearity and time shifting properties. Now what we can do is to find the actual x1 of n signal. So basically we can perform the inverse z transform of this particular signal, x1 of z, right? So this is the signal. If we use the causal properties again from the signal, we can see, use the causal properties on from the page 170 of the textbook. You can see using this property, this is a causal property, right? So a of n is, using this particular property, right? This number 3 property, we can find x1 of n is equal to negative half to the power of n u of n, right? So this is the inverse z transform of x1 of z. This is the causal signal that we get. Now we can take this signal and substitute it into this x of n signal to find the actual x of n signal. So basically x of n is equal to, in place of x1 of n, we replace this particular term. It is negative half to the power of n u of n. Then it is minus, so we keep the minus, right? We keep the half, 1 half, right? And then in place of x1 of n minus 1, right? So in place of x1 1 of n, in place of n we substitute n minus 1. So, and we then substitute that into this particular term. So we'll get negative half to the power of n minus 1 u of n minus 1. So basically this particular term is delayed by 1 unit and it is multiplied by negative half. So that is what we get over here. So basically the overall x of n signal can be rewritten as this particular term over here, right? Then for j, x of z is given as 1 minus a z to the power of negative 1 holding upon z to the power of negative 1 minus a. Right? This is the term that we are given over here. What you can do is, again, we can rewrite it, right? We can keep the numerator as it is, right? And we can substitute x1 of z is equal to 1 upon z minus 1 minus a, right? This is using this substitution, using this particular substitution, we can rewrite this particular term over here as 1 minus az to the power of negative 1. This is the numerator as it is, and then multiplied by x1 of z. Right? Using this particular substitution, we can rewrite this as this. Now, performing the inverse z transform of these in terms of x1 of n, this signal can be written, x of n can be written in terms of x1 of n as this, right? x1 of n as it is, remember it is multiplied by 1, so inverse z transform of x1 of z will be x1 of n multiplied with x1 of z expanded into this particular bracket, we'll get x1 of z multiplied by negative a multiplied by z to the power of negative 1. So basically, a is just a constant, this negative a is just a constant, so we keep negative a as it is, right? And this z to the power of negative 1 indicates it is delayed by 1 unit, right? Time shifting property, right, over here in this particular case. So what we get x1 of n, it is delayed by 1 unit, so n minus 1, right? Now our job is to just find this. Our job is to find x1 of n. So basically, we just need to perform the inverse transform of this particular signal over here, right? So if we perform the inverse transform of this signal, right, and using the properties that is given in your on your textbook, the causal signal properties, right? Or again, or what we can do is or just using this the properties that are listed in the question above here as well, right? We can use this particular property and find the inverse transform of this. So basically this particular term, right, x1 of z can be read one x1 of z is equal to 1 upon z to the power of -1 minus a can be rewritten as this over here, right? This is the signal we get. Based on this, using this property over here again, this -1 upon a is just a constant, so we keep it out, right? And then we can find the inverse Z transform of 1 upon 1 minus 1 upon a z to the power of -1, right? Whatever we have, we find the inverse Z transform. So this is the term we're getting. And we can further simplify it and we can rewrite it as this, right? So once we have x1 of n, we can substitute x1 of n into this particular term to get our x of n. So x of n is basically equal to -1 upon a to the power of n plus 1 multiplied by u of n plus 1 upon a to the power of n minus 1 u of n minus 1. So you can see there's a trend. Whenever you have a u of n or u of n minus 1 or n minus 2, whatever variable we have, as long as we have a u of n, right, as it is, delayed by some particular unit, it is a causal signal, right? Just remember that. If in case if the signal is multiplied by u of -n, delayed by some other unit, in that particular case, what happens is that signal becomes anti-causal, right? So just remember this. This is just a quick property that you can remember. So moving on to the next question, 3.15. Again, 3.15, determine all possible x of m associated with Z transform. Right, this particular Z transform over here that we are given over here, we need to find the in x of n. So we have to find all possible signals that will give us this Z transform of this particular part, right? So what we have to do is in this particular case, we have to consider all the anti-causal, the causal signal, and the region of convergence determined by this anti-causal and the causal signals altogether, right? So in this particular case, we'll be having three different region of convergence, right? So what we can do is first thing is to rewrite or decompose the signal that on hand using the partial fraction. We have to write it into a partial fraction form. So decomposing that, we'll be getting 1 upon 1 minus 2 z to the power of -1 plus 1 upon 1 minus 1/3 of z to the power of -1. Right. So this is the term that we are going to get. So based on this, you can see, right? Based on this, you can see the modulus for this. In order for the region of convergence to be defined for this particular term, right? For the first term, right? Let's say this is term 1, this is term 1, right? This is term 1, and this is my term 2, right? So let me write T2 and T1. So for term 1, right, my region of convergence would be absolute of z is greater than 2. For term 2, it will give me absolute of z, or the modulus of z is greater than 1/3. Let's keep this as it is, right? So we know this, that from this particular term, we have absolute of z is greater than 2. And from this particular term, we know that z is greater than 1/3. So now if we make the region of convergence of this particular for both the terms and the overall z transform of these, right? If we draw the region of convergence, so we have 1/3. Let's keep it over here, and then we have 2 over here. Right? Let's keep it over here. So if we draw, so this the inner circle is 1/3, right? Has a radius of 1/3. The outer circle has a radius of 2, right? So based on both of these definitions, for the signal to be causal, it has to fall on the outer side, right? So just in case for a causal signal, it has to fall on the outer side. So the overall, in order for the signal to be causal, for the overall signal to be quotient, it has to be greater than 2, isn't it? It has to be greater than 2, right? For all this portion over here, right? So it has to be quotient on this all this area, right, over here. So basically the overall, in order for the signal, in order for this particular signal to be causal, it has to be greater than 2, right? This particular the condition of term 1 outweighs the condition of this particular term, right? So then in that particular case, the overall region of convergence of this particular term is, in order for this signal to be causal, the modulus of z has to be greater than 2, right? So in that particular case, again using the causal properties, we'll be getting, right? Oh, there's an error over here. This one, suppose this has to be just oh, this term over here was supposed to be negative, not plus, right? Okay. Okay. This part has to be negative, not positive, right? It has to be negative. Just let me quickly line this over here has to be negative, not positive, right? So we have this particular term, right? So this performing the causal properties, I mean, using the causal properties that is given on here. So on page 170 here, using the properties over here on this page number 170 of the textbook, right? You can see we'll be getting 2 to the power of n, right? The inverse Z transform of these 2 to the power of n minus because they're negative, minus one third to the power of n u of n, right? That will be the causal signal, right, of this particular Z transform, right? Now, for the signal to be anti-causal, it has to fall on the inside of the signal has to fall on the inside part, okay, inside the circle. So it has to fall on the inside of the circle. Let me just draw it. For the overall signal to be anti-causal, it has to fall on the inside of the circle. You can see it if it falls on this particular part, right? So the overall, for this term to be overall anti-causal, it has to be inside this particular circle, right? Because this, in that particular case, term 2 outweighs term 1. The magnitude, I mean, the condition of term 2 outweighs the condition of term 1 for the signal to be anti-causal, right? Because this term says for this term to be anti-causal, it has to be less than 2, right? It has to be less than 2, right? For this particular term, for this particular signal to be anti-causal, it has to be less than 1/3. So the overall for this particular the anti-causal signal for this particular Z transform has to be less than 1/3 for this whole signal to be anti-causal, right? In that particular case, again using the Z transform properties, it will be negative A of n. So whatever we got, negative A of n. So in this particular case, the Z transform of this, the anti-causal signal of this particular Z transform will be negative 2 to the power of n, right? Now over here it was positive 2 to the power of, now it will be negative 2 to the power of n multiplied by, now it will be u to the power of u, right? So multiplied by u of negative n minus 1. You can see, like I had earlier mentioned, if we have a negative n, right, but multiplied by u of negative n, it becomes an anti-causal signal, isn't it? So in this particular case, we are multiplying with a negative u of negative n, and the signal has now the inverse, right? Whatever value we got over here in the causal system is now negative value of that, right? Negative 2 of negative 2n, right? Now, the anti-causal signal for this particular term over here is going to give me 1/3 to the power of n. It was negative 1/3 earlier on, right? Because of this negative, now it has changed into positive. So now it will be positive 1/3 and u of negative n minus 1, right? So this is the term that we get for the anti-causal signal. If this signal was, I mean, the x of n signal that we obtain, right, the z transform that we have, the anti-causal signal of that will be this particular signal over here. Now, if you let me just quickly check. Now, what happens? We have already covered. Let me clear the point. Let me see it first. Okay, so there's a signal here. Hold on. A small signal inside. Now we have covered what if the signal was causal, that was outside this larger circle, or if the signal was anti-causal, that would be the region inside the smaller circle. Now we also have a condition, what if the signal, the region of convergence is between these two circles of here, right? In that particular case, we can see we have the anti-causal property of the outer term, that is term 1, this particular term, the anti-causal of this particular term signal, and we have the causal signal. It falls on the outside of this inner circle, so that is the causal signal of this particular term over here. So it is combination of the anti-causal of this particular term and the causal signal of this particular term. So we get the anti-causal signal of this particular term is minus 2, right? Minus 2 to the 2n, right? You have the minus and then 2 to the power of n, right? Basically just introducing minus in front of 2n, right? U of minus n minus 1, right? This is the term. We get the anti-causal signal of this particular term and the causal signal of this second term over here that we have. So that is negative, negative as it is, negative comes in front, or we can assume that the constant multiplication is negative 1. So negative, right, of the causal signal of this particular term over here, 1 upon 1 minus 1/3, z to the power of negative 1 is 1/3 to the power of n, so that is 1/3 of the n multiplied by u of n. So this is the term that we had. Get if this z value is between this particular region. The region of convergence is between these two circles, right? So that is how we get these three signals over here, right? Now, moving on to the next question, 3.18. 3.18, let me go back to the question that is on page. Okay, 3.18, we have made to solve for all this. This is basically proving all these particular properties over here that we are given on hand, right? So the first property is to prove that the Z transform of x conjugate n is equal to the what do you say, x of Z conjugate, the whole thing conjugate again, right? So basically we need to prove this. So in this particular term, using the Z transform property, again perform the Z transform of x conjugate. It is directly taking that and substituting into the Z transform definition. We get this, and then taking this conjugate out, right? If we take out the conjugate out, we can see that x of n, this conjugate has been taken out, so conjugate is out. Now if we take the conjugate out, this Z as now will be introduced with the conjugate, right? So we have to perform the Z conjugate of this, because this conjugate and this conjugate will give us the original signal, and conjugate of a conjugate is going to give us the actual signal, right? Or just a conjugate performed on an actual signal will just be a conjugate of it, right? So again, if we take out the conjugate out, we'll get this particular term, and then you can see this inner term is just the Z transform, but in place of Z it is Z conjugate. So that is what we have over here, and this conjugate is introduced over here. So overall, once we have performed the Z transform in terms of x of Z conjugate, we have to perform the conjugate again, right? So this is what we get over here. Again, for the signal, going back over here, this is a transform of real part of a signal x of n is equal to half into x of z plus x conjugate of z conjugate, right? This is what we get over here. Again, like I said, in this particular case, what we can do is we can perform the z transform of this signal, right? Oh, okay. Z transform of this real part of x of n could be rewritten as z transform of the real part of x of n could be rewritten half into x of n plus x conjugate of n, right? So yeah, so this real part of x of n could be rewritten as half into x of n plus x conjugate of n, right? Remember, this part will give us real plus imaginary part plus the conjugate of that will be real minus imaginary part. So the plus imaginary and the minus imaginary will cancel out. Real plus real will give us 2 real, so we'll have twice the real value of x of n. So we need to half it in order to get the real of x of n. So that is how we get this particular part over here, right? This is simple mathematics. So we can rewrite this transform of real in terms of this particular term over here, and then performing this transform of this signal that is going to give us half is just a constant, so we can take out this half will be outside, right? And then z transform of x of n is going to give us x of z, right? And then z transform of x conjugate of n based on the property that we have investigated earlier on over here in part A. Using this property, we know that the z transform of x of n conjugate is going to give us x conjugate z conjugate, right? This is the particular term that we get. So based on that, we can prove that the z transform of real part of x of n is equal to half into x of z plus x of z conjugate and conjugate of that, right? So that is what we get as the z transform of real part of x of n over here. Next is to prove that the z transform of that imaginary value is equal the imaginary value of x of n is equal to half into x of z minus x conjugate of z conjugate. I mean x of z conjugate of that, right? So again, using the same thing, we can rewrite this imaginary of x of n as 1 upon 2j into x of n minus x conjugate of x of n, right? So this is what we can rewrite this imaginary of x of n is this particular part, and then we can perform the z transform of the z transform of that particular term over here, right? So if you perform the z transform of this, we'll be getting 1 upon 2j is just a constant, so 1 upon 2j can be written as that. Z transform of x of n is just going to give us x of z minus, again, z transform of x of n conjugate is using the properties that are given in this particular part over here, in part A of this particular question. We can get this particular term over here. So we have proved that the z transform of imaginary of x of n is equal to this part over here, right? Then part D, if x of n k, right? Kth value of x of n is equal to x of n upon k, right? If n upon k is an integer value, 0 otherwise, right? So based on this, what we can do is again just using this simple definition of z transform, we can directly substitute that. So based on that, if we do the z transform of that, we'll write it using the z transform definition, we'll get this bit passed, and then we can substitute m is equal to n upon k. We'll get this particular part here, which is equal to x of z to the power of k, right? So again, we have proved that. Then moving on to part E, right? Part E, z transform of e to the power of j omega naught n multiplied by x of n is equal to x of z e to the power minus j omega naught, right? So we basically prove that. So again, using these transform properties, we can just perform these transform of this particular signal that we have here. Using this transform definition, we can rewrite that as this, right? And then again, we can group these two terms over here, e to the power of j omega naught n with z to the power of negative n. We can regroup it as 1, so we can regroup it again minus n, this whole term. So it is basically z transform in terms of e to the power of minus j omega naught z, right? Question number 3.23, right? 3.23. Determine the signal x of n with z transform. X of z is equal to e to the power of z plus e to the power of 1 upon z, right? Where magnitude of z is not equal to 0. So basically, the signal is a causal signal in this particular case again, right? So based on this, using the how do you say the properties of the exponential expansion of this particular term e to the power of z, or the property of exponential expansion that e to the power of x is equal to summation of x of n upon n factorial, right? Sum from 0 till infinity. So it is just using this particular property, we can rewrite this x of z as these two terms over here, right? And then we can further simplify it. We can further simplify this, and we can see that we can rewrite it as this particular term over here. And further simplifying, we get summation of summation from negative infinity to infinity of 1 upon n factorial multiplied by z to the power of negative n plus 1, which is equivalent to the inverse Z transform of this, right? Inverse Z transform of this is going to give us inverse Z transform of 1 is just going to be delta n, right? And the inverse Z transform of this is just going to give us, remember, this is in terms of the Z transform definition part. So this particular signal over here, 1 upon n factorial, is just our x of n. So x of n in that case is 1 upon n factorial, right? So this is what we get for the inverse Z transform of this particular signal over here. Okay. Moving on to the next part, question number 3.24. Question 3.24, determine in enclosed form the causal signal x of n whose Z transforms are given by, so these are the Z transforms that are given over here. So A and B are given. So what we need to do again, we need to, we can see that this particular part A, we can rewrite the signal using the partial decomposition. So using the partial fraction decomposition, we can rewrite the signal in terms of this, right, over here, and then perform the Z transform in the inverse Z transform, the causal signal of that. Did you say causal? Yeah, it is a causal signal, right? We need to determine the causal signal x of n. So using the Z transform properties given on page 170 of your textbook, we can find the Z transform of this particular signal over here as x of n is equal to 0.136 multiplied by 0.28 to the power of n plus 0.864 into negative 1.78 to the power of n multiplied by u of n, right? The whole signal is multiplied by u of n. For part B, x of z is equal to 1 upon 1 minus 0.5 z to the power of negative 1 plus 0.6 z to the power of negative 2. We can see we can not decompose this signal into what do you say? We cannot factorize this particular denominator in this particular case. So rewriting this into partial fractions would be difficult. So going back to page 170 of your textbook, right? 170 of your textbook, you can see that we have something similar to that, right? So the term we have over here, it is in terms of z to the power of negative 2, z to the power of negative 1, and 1 itself. So we can see that we have two terms that have that. So we have a cos omega naught n cos of omega naught n multiplied by u of n gives us this particular Z transform, and sine of omega naught n is going to give us this particular Z transform. So what we can do is manipulate the equation in a manner so that we can rewrite this signal the inverse Z transform in terms of cosine and sine, right? So manipulating that will get this particular form. So and then we can manipulate it to get this, and we can rewrite the inverse Z transform of this particular signal as in terms of cosine and sine as 0.7746 to the power of n holding multiplied. I mean, this term multiplied to the term cos of 1.24n plus 0.3412 multiplied by sine 1.24n holding multiplied by u of n. So this is particularly the inverse transform of this Z transform that is given to us, right? You can check whether this Z transform that we have obtained is accurate or not, or verify using partial check. So if we find x0, x0 of this particular term, we'll get 1. x1 x of 1 of this particular signal is equal to 0.5016, and x of 2 for this particular signal is going to give us negative 0.3476, and x of infinity is basically equal to 0, right? So based on this, because y it is equal to 0, any decimal number raised to the power of 0, so the number of decimal places increases, isn't it? So 0.0000 something. So basically it approaches 0, right? Just because of this particular term over here. So this is what we get if we perform a partial check on this particular part, and then we can use the partial difference equation over here. So if we take this denominator and multiply it to this particular side, so we get x of z minus 0.5 z negative 1 multiplied by x of z plus 0.6 z to the power of negative 2 multiplied by x of z, right? So basically we get that is equal to 1. So there is the partial differential. Better simplified of that, and then what we can do is to find the inverse transform of that signal that will give us x of n minus 0.5 x of n minus 1 plus 0.6 x of n minus 2 is equal to delta n, right? So now what we can do is to evaluate this particular part. We can see if it's a causal signal, it will fall on the right hand side of the on the positive side of the real axis. So in that particular case, it includes 0 and all the positive values. So in that particular case, x of 0 is going to give us all these terms x of n minus 1. So x of negative 1 is going to be 0, x of negative 2 is going to be 0. Assuming that we get x of 0 equal to delta n, that is basically equal to 1, right? X of 0 is equal to 1. And then finding x1 of this particular signal, will be getting 0.5. x2 is equal to negative 0.25, and x of infinity is basically equal to 0. So basically this particular part is approximately equal to this particular part over here. So basically in that particular case, the inverse Z transform that we have obtained by manipulating this equation and rewriting in terms of sine and cosine is equivalent, right? In that particular case, that was two. Okay, so that was for particular question right over here. So we had performed this partial check here, so by computing, so we have already done this, right? Now moving on to question number 3.25. Question number 3.25. Determine all possible signals that can have the following Z transform. Again, we have these two signals given over here. First step is to perform the for part A. So this is the Z transform that is given, and we have to find the all possible signals that are going to give us this particular Z transform. So in that particular case, we can see that we can decompose this this denominator as 1 minus z to the power of -1 into 1 minus 0.5 z to the power of -1, right over here. This. So we can further rewrite it as in terms of the partial fraction form as this, right? So we can rewrite this z transform is in terms of partial fraction as this. That is 2.1 minus z to the power of -1, holding minus 1 upon 1 minus 0.5 z to the power of -1. Okay. This is just performing the partial fraction decomposition of this particular term over here. So again, in this particular term, you can see that wait one second, is the okay, I can see that okay, the equation of convergence for this term is that is equation of convergence for that is greater than 1, and the region of convergence for this is z is greater than half, right? So region of convergence of this is greater than half. The region of convergence for this is greater than 1. So we have 2. So if we draw the region of convergence, we have 2 circles. That is, one is on half, right? One is at half, and the other one is at 1. So in order for the overall equation to be causal, this has to fall on the outer part of this larger circle. That is, the absolute of z is greater than 1, right? So z value has to be greater than 1 for the signal to be causal. The next is for the signal, the overall terms to be causal, it has to be less than half, right? It has to fall inside of this smaller circle, and the other term would be the signal that falls inside this region, the region in between those two circles, right? So the anti-causal signal that gives us this particular z transform, or performing the inverse z transform to find the anti-causal signal using the properties that is given in your textbooks, page number 170. We get x of n is equal to 0.5 to the power of n minus 2, whole multiplied by u of negative n minus 1, right? What if the signal is causal? So the causal signal that gives us the z transform of this, that is basically z is greater than 1, like I said. In that particular case, the causal signal would be x of n is equal to 2 minus 0.5 to the power of n, whole multiplied by u of n. You can see next is, what if the signal falls between these two regions, right? Between these two circles inside this region over here. So you can see it is basically the anti-causal signal of this outer circle term. So that is the anti-causal signal of this particular term, and plus the causal signal of the term that has a region of convergence that falls on this particular circle, right? Now depends on this particular circle, that is of this particular term over here. So basically, it is a combination of the anti-causal signal of this particular term and the causal signal of this particular term. So the anti-causal term of this particular term would be minus 2 u of minus n minus 1, right? And the causal term of this particular term would be negative of 0.5 to the power of n, right? So these are the three possible signals that are going to give us the z transform as this, right? So that's for that particular part. Again, for the second part, again doing the same, we can decompose it in terms of I and j into the real and imaginary part, and we'll be getting this big part, and performing z transform again, we'll be getting this terms over here, right? And then again, like I said, it will be having the region. You have to determine the region of convergence, and based on that you can find the causal and the anti-causal signal, right? If you go back to your textbook, the solution given for that question would be 3.25, right? So we have two regions, and that is what we are getting over here from this particular term over here. So it is slightly different over here in this particular case. It is given in terms of the imaginary real and imaginary signal. In this particular part, in the textbook, it is given in terms of this. So that is in 3.25. Is it 2.5? Okay. Okay, that solution is not over here. It is dealing with a completely different part here. So okay, anyways, you can decompose this signal. Right. You don't have to go the hard way. This signal is dealing with plus. This signal is dealing. You don't have to go the hard way that has been used as over here. You can basically use this method, right? You can rewrite that particular term over here. You can rewrite this whole term. You can see that this denominator could be rewritten as 1 upon 1 minus 0.5 z to the power -1 holding square, right? And based on that, you can further simplify this as this, right? Over here, the term over here. And then based on this, we can use the anti-causal properties that are given in the textbook. Based on that, we get these two signal up here, right? It is for z is greater than 0.5 because it is a repetitive. So basically, the region of convergence would be either, if you draw the region of convergence for this, right? That would be just a circle of radius 0.5, right? So there could be two possible signals that are going to give us the Z transform as the term given on the textbook, right? So this particular Z transform over here, that is first if Z is less than 0.5, right? That is the anti-causal signal. In that particular case, we get -n plus 1 multiplied by 0.5 to the power of n, wholly multiplied by u of -n minus 1. So there is the anti-causal signal. On the other part is if z is greater than half, that is falling on the outside part of the signal, right? So in the particular case, we'll get this particular term over here, the inverse transform is that, right? Anyways, now moving to the next question, that is so please don't use this. You can I believe you can simplify this part, right? And simplify it. You don't have to write it in terms of ing. Then there needs to be a correction over here, right? Anyways, okay, so you don't have to use this. Please use this solution over here. For 3.25b, right? This is the solution that is given. That should have been given, right? We can decompose this particular term here as we can decompose or factorize this denominator as 1 upon 1 minus 0.5 z in z of -1 holding square, right? We can factorize this. So we factorize this, and we can rewrite this term as 1 upon 1 minus 0.5 z to the power -1 whole thing squared dot as this, right? So this solution is not applicable. So we should be using this particular part, this particular solution for this particular part, right? Moving on to question number 3.28, that is the last question for this week's tutorial. The rest of the tutorial questions will be covered into the next next week's tutorial, right? 3.28, prove the conjugate properties and the conjugation properties and possibles relation for Z transform given in table 3.2, right? So table 3.2 to table 3.2. So we need to basically prove those properties. 3.2. Okay, these properties are given over here. So basically the main properties are these possible property that we need to prove and the conjugation property, right? These two properties, the conjugation property, the conjugation property is not given. So basically we just need to prove the possible property because we have already proved the conjugation properties, right? It is given. So let me just check the question again. Yeah, we just need to prove the possibles theorem and the conjugation property, right? Based on the question. Anyways, the conjugation property we have already proven in question number. Now we have already touched on that in question number 3.15, I believe. Yep, we have proved the conjugation property over here, so no need to do that, right? So I'm not going to go over that again. But just on the possibles theorem, possibles relation, you can see that based on the possibles relation that is given on page number. I just go on 2.2. Okay, we just need to prove this possibles relation over here, right? So based on the possible relation, it is x1 of n multiplied by x2 or conjugate of that, right? And summed from negative infinity to infinity. So we just need to prove this particular part of here, right? We have. So if we prove that, in order to prove that, we can start off with this particular term over here. We can start from here. And we can start from here. So we can rewrite this x1 of n using the inverse Z transform property, right? So let's say we have x1 of Z. Performing the inverse Z transform of that, it says that x1 of n will be given by 1 upon 2 pi j. Contour integration, counterclockwise contour integration of x1 of z to the power of negative z to the power of n minus 1 dz, right? That particular property you can find it on your textbook. Let me just go and show it to you from your textbook. Inverse Z transform. Okay, yeah, based on this you can see that inverse Z transform is given by check so you can see that on page 180 of your textbook, the inverse Z transform of a Z transform signal could be given as this particular term, right? So basically you can obtain x of n by performing the contour integration of x of z multiplied by z to the power of n minus 1 and whole thing of that multiplied by 1 upon 2 pi j, right? So this using this particular property we can rewrite we can rewrite x1 of n, right? So we can rewrite that using the property that is given on your textbook, page number 180. We can rewrite x1 of n. So we can keep this particular part. We can keep it as it is. We can rewrite x1 of n using the inverse z transform property. That is 1 upon 2 pi j anti-clockwise contour integration of x1 of z multiplied by z to the power of -1 dz, right? And we can keep this particular term since we can assume that this is a constant, right? As it is, we can keep it as it is, right? Now, based on this, if we further simplify this, right? If we take this, now what we can do is we can treat we can treat the summation of x2 of n conjugate of that summed. We can take this term and we can take this term over here and perform the summation of that, right? If we perform the summation of that, remove this, right? There should be n, right? So if we take this and perform the summation of that, and while we can treat this term, this, right, as a constant, right? And if we do that, we can treat this term, right? We can take it over here and the integral as it is dz, right? And we can treat these two that marked with underlined with red as the summation, right? If we perform the summation, right? So we can perform the summation of this. So we get this right over here. So you can say that, see that this is just basically another way of writing the Z transform. It is similar to your Z transform definition, but in place of Z, it is 1 upon Z, right? So that is basically x2 of 1 upon Z conjugate of that, right? This particular term could be written as this over here. And we can rewrite this, take this particular term and rewrite it as it is and bring this dz over here and this z minus 1. So basically it is proof that this the summation of x1 of n multiplied by x2 of n conjugate is basically equal to this using the Parsifal's relation, right? We have proven the Parsifal's relation using this, right? So remember, there's an error in the solution. Again, this final solution should be having z to the power -1, and then over here there shouldn't be any error, right? So we first thing is to rewrite x1 of n using the inverse transform definition or the contour integration, right? Formula. So we can rewrite that, right? We can replace x1 of n in terms of x1 of z. So there we go over here, and then we can, next thing is we can basically perform the summation of x2 of n conjugate into 1 upon z to the power of -n, right? So from that we can see that we get this particular part of here, and remember this z to the power of -1 has been taken outside. Okay, so that's how we get this particular part over here. So that's it for this fixed tutorial. See you next week, right?